Have you ever wanted to know what the temperature is? In the past?
Temperature and time.
The temperature happens through time.
See, a regular thermometer can tell you if it's hot or cold. But I can't remember the past. I can't remember anything. I can't remember anything! I went camping in cold weather recently, and I wanted to know how cold it got during the night to gauge how effective my sleeping gear is for different temperatures. I looked online, and I found these temperature loggers meant for testing your refrigerator.
These would be fine if it weren't for the fact that you need to download a goddamn app to view the data. I am so sick and tired of downloading all these greasy apps onto my phone. They only serve one purpose, probably charge a subscription fee, and will eventually stop working entirely.
It makes me sick. It makes me sick!
How hard could it be to make one on our own? It just needs a temperature sensor, a battery, and a screen, right?
I really wanted the display to be e-ink because I thought it would be cool if it was always on, unlike these other backpack sensors where you need to push a button to turn on the display. Conserving battery life was going to be the #1 challenge for this entire project, and e-ink displays don't consume any power when the image isn't changing, so it's pretty much perfect. They also have high resolution, and I really liked the idea of showing the current temperature as well as a history graph.
Now for the microcontroller, we need something that has enough juice to quickly render the user interface, consumes very little power, and is physically small. There's plenty of really good microcontrollers meant for mobile devices to choose from here, and ESP32 it is. An SoC like the NRF 52840 might have been a better microcontroller for an application like this, but the ESP32 really is the sledgehammer of microcontrollers. That is when you're a silly goose like me. When you're stupid, right? It's powerful, cheap, and easy to design around, and it's actually pretty good on battery when you use the deep sleep mode.
Plus, the S3 Mini module does have a Bluetooth antenna if we decide to make an app after all.
Slap it on the PCB!
A quick tangent. When I made a post about this project on the Arduino subreddit, I got a lot of comments and messages from people asking me how did I figure out how to make my own microcontroller board. Well, the answer is a lot easier than you might think. So basically, you're just going to want to go to this website called Adafruit.com or SparkFun, and you're going to want to find a board that does something similar to what you want, go to the schematics, and then you're just going to hit copy and paste it into KiCad like this. In all seriousness though, unless you're doing something with high data speeds, most beginner digital PCB design is as simple as referencing the recommended implementation diagram from the datasheet, or a reference design like these open source boards from SparkFun. It's great to watch YouTube videos to learn how to do something, but if you actually want to get something done on your own, the real answers to all your questions are right there in the datasheet. You just have to slow down and take the time to read them.
This is pretty much what I did for the battery charging and power management circuit, because if you just search up battery charging IC into DigiKey, you're going to find thousands of results. You'll spend hours searching through dozens of similar datasheets and then just give up because of the completely overwhelming choice of a microscopic circuit board chip that's supposed to help charge a battery and an overly complicated thermometer that you thought would be easy to make and you don't actually need, but you just get so cold in your sleeping bag at night. And you can't remember what the temperature was because I literally can't remember anything. My brain doesn't work. I can't remember anything at all. What's going on?
So, instead of doing that, I'm just going to copy the battery babysitter board from SparkFun because it seems to work and it uses popular components. This circuit includes a battery management chip that switches the power path of the device between the battery and USB power depending on if we connect a charging cable. It also charges the battery when plugged in with configurable charging rates and can signal to our ESP when charging is taking place. The fuel gauge continuously monitors the current flowing in and out of the battery, which gives a more accurate indication of the battery percentage than simply checking the voltage.
Slap it on the PCB! Unfortunately, this still isn't enough to directly power the 3.3 volt ESP32 because LiPo batteries can actually reach 4.2 volts when fully charged, and the battery thingy doesn't actually regulate the output voltage. I kind of just stumbled upon this regulator that has enough juice to power the ESP with decent efficiency and doesn't require a bunch of extra crap on the board to work properly. One problem you have to look out for when choosing regulators is that while many have very high efficiency, they can also have high quiescent current. That means that even though under load they'll have amazing efficiency, they'll still draw a small amount of current at all times, even when nothing's really going on. And that's a problem for this board because we need to make this 450 milliamp battery last over a week, and that really adds up. Okay, so we'll obviously need a temperature sensor, right? Well, this one's accurate, small, and even doubles as a humidity sensor. Toss it on the PCB. Toss a couple buttons on there too. And a USB port. And a TVS diode.
Now, one issue with e-ink displays is that unlike OLED modules, we can't just give it power and data and be done. It needs an analog boosting circuit to update the screen, and the hobbyist display driving boards are way too big. I have no idea how this actually works, so we're just gonna go to this website called waveshare.com.
Okay, so we've got a computer chip, battery stuff, sensors, and a screen. We're done, right?
No.
We need to talk about how we're going to pull off over a week of battery life with this design. See, I mentioned that the ESP32 has some deep sleep features, but they come with some caveats. The ESP32S3 draws enough current to kill our little battery in like 2 hours. But with deep sleep, it draws less than 1 milliamp, which is effectively like it's turned off. In fact, it literally does turn off the CPU, which causes the program to stop running and forget all our temperature history. And once it turns off, the software can't run anymore, which means that it can't respond to button presses, which means it'll just stay off indefinitely. Fortunately, the ESP32 has wake-up sources, including a real-time clock. So, if we want the screen to just wake up once per minute, then we'll just enable the clock, right?
No, that'd be easy. And makes sense. If it were that easy, then I'd be happy with, I'd love myself, and then my life would be good, right? Can't have that.
See, the ESP32's real-time clock is shit.
Dog shit.
Well, no, it's just not good enough to keep accurate time over a week, so we're gonna have to add more stuff to the PCB.
Yay! Woo! Yeah! I love DigiKey. I love DigiKey.
The DS3231 is a classic low-power timekeeping IC that we can leave running while the ESP32 is sleeping. It also has these built-in alarms, which means we can completely power down the RTC peripheral on the ESP32 and then just use these alarms on an input pin to wake it up once per minute. Slap that beautiful boy on the PCB. Slap that cocksucker on the PC. The other problem with constantly rebooting the ESP is that we need somewhere to store our temperature history and program state so it doesn't get deleted. So let's add an external EEPROM as kind of like a hard drive to store that data. It's designed for repeated write cycles and could last for years with non-stop usage without wearing out.
And I know that some of you are already in the comments like, yo, why don't you just use the large flash already on the ESP32 with a wear leveling library to solve that?
First of all,
I don't know you, and I don't have to tell you anything.
but to answer your question, what else would I put on this empty corner of the PCB? Fuck it. Slap it on the PCB anyway. Alright, so now we have to decide if there's going to be a way to completely power down this device, or if it will always just kind of be on. I decided to properly do it, but I still wanted the PCB to be the same size as the screen. And I've got no room for a crusty mechanical switch. I need that space for my gigantic EEPROM. So let's add a soft power button, similar to how your phone's power button works.
Our power path IC actually has an input specifically for this purpose. It disconnects power from the entire system. I spent way too long trying to find a way to use logic gates to latch the on-off state using the buttons. I wanted the ESP to power off the system, then be energized by another button press. But as usual, I just found an IC specifically designed for this exact purpose and just used that instead.
The LTC2954 is a button on-off controller. It runs directly off our battery, uses almost no power, and manages the on-off state of our power path IC. It also forwards the state of the button to the microcontroller, so it still works normally in our program. The ESP can also trigger a shutdown via software. When the IC is in its off state, an additional button press will turn it back on. And when the ESP is about to go to sleep or shut down, we can write whether it's about to completely shut down to the EEPROM. Then, when the ESP turns back on, we can reference that EEPROM data to determine if the ESP is freshly starting up from a complete power off, a minute interval wake up, or if the user is just interacting with the buttons normally in its on state.
The fuel gauge, clock, and temperature sensor are all I2C devices. That means we can just connect them all to the same data bus on the ESP and use pre-made libraries to control them. The display gets an SPI connection, then we just connect our wake-up sources and a sense resistor to know if the charging cable is connected or not, and we're done.
All you need to know is that we're holding on. We rise up from the dust and clean my throat.
This board is definitely not perfect, but surprisingly, it worked on the first try. I had to order assembly on this one because the components are too small to hand solder, and the only real mistake I made was forgetting a pull-down resistor, which my engineer coworker was able to tack on for me. I wanted the case for this device to be as small as possible, so I actually ended up getting an entire new 3D printer specifically for this project, because the 3D printer that I made in high school just didn't really have the quality I was looking for anymore.
Usually I make my models in Fusion, but for this one, I decided to use OpenSCAD because I have no idea what I'm doing. I can't remember. And I knew that I would need a ton of iterations to get everything to fit perfectly.
And since OpenSCAD is code-driven, it was easy to drive the proportions and tolerances of the entire model with a big list of variables. It makes the whole thing parametric, so I can change one of these numbers and the rest of the model updates automatically.
So the final step is to write the ESP32 code, and I know nobody actually wants to see any of that, so basically the software works by waking up once per minute from the DS3231, it immediately takes a temperature reading and stores it to EEPROM. Then it updates the screen and goes back to sleep as soon as possible. That brief process is what consumes almost all of the power, because even though it only takes a couple of seconds, the ESP can pull 50 milliamps while it's doing this.
It's important to read the temperature first, because the ESP generates so much heat during this step that it actually heats up the temperature sensor through the board and lowers its accuracy. In fact, whenever you're holding the device and keeping it awake by going through the menus, the temperature reading will be inaccurate for multiple minutes until it cools down. Even just the heat from your hand messes it up, or if the sun is hitting it, or if it gets too close to your body, then it's no longer measuring the ambient air temperature.
Also, the display isn't rated to work below zero, so while we can log those temperatures, we can't display any of them until it heats back up again.
There's definitely some flaws and limitations with this thing, but I've been pleasantly surprised with how reliably it's been working so far.
I've even brought it on a few hiking trips, and now I always know what happened in the past. I'm open sourcing this project. The firmware has some quirks, and there's definitely more that could be done to increase the battery life even further, but it pretty much already does what I want, and I'm a busy guy, and I'm not smart enough to solve any more of the problems, so it's done. Calling it there. If you want to see more projects by me, then please subscribe to my YouTube channel. We're on our way to hit 10 subscribers, and I know we can do it by the end of the year. Please subscribe to my YouTube channel. Please subscribe to my YouTube channel. Please subscribe and hit the bell. Yo, please hit the bell.